Good morning and welcome back. As I mentioned, this Tuesday, I told you I will go on a hike for 3 days. I wish to reach the summits of 4百岳、大坝尖山、小坝尖山、伊泽嘉利山. So today's classes will be changed to the online learning. I will post everything on the YouTube. Okay, so let's begin. I will talk about chapter 3. We will solve the boundary value problems. Second part, that's the electrostatic. Electrostatic, part 2. Many students remember this figure, these photos, because they say this is Dirac and this is Feynman. They are surprised to know Dirac, the size of his head and his body, almost about 9 times. Beauty. Okay. I want to talk about Dirac and Feynman's opinion on solving the problems, because we are going to deal with a very difficult problem. Legendre polynomial, Legendre equation, associate Legendre equation. That's complicated. The purpose of solving this equation is to expand the green function into a complete function set. That's our purpose. So we are going to expand the simplest green function in Cartesian coordinates into spherical coordinates and cylindrical coordinates. That's our purpose. But how to do that? To do that, we have to solve a very difficult problem. We have to solve Legendre polynomial, Legendre equation, and associate Legendre equation. We should consider all the possibilities. That's a little bit complicated. So today we will start with these two comments first. Dirac say, I understand what an equation means if I have a way of figuring out the characteristics of its solutions without actually solving it. So Dirac do not solve the equations. On the other hand, he wants to know the equation's characteristic, its behavior. And a physical understanding is a completely unmathematical, imprecise, remember, and inexact thing, but absolutely necessary for a physicist. Let's quote it in Feynman Lectures on Physics, 2nd volume. So I will say this word again. A physical understanding is a completely unmathematical, imprecise, and inexact things. So we should learn its characteristic first. Characteristic of the equations first. Okay, we will start with the Laplace equation. Laplace equation with source free. And we will express in spherical coordinates, r, theta, and phi. So in terms of spherical coordinates, Laplacian can be written into this form. 1 over r partial square, partial r square, r times phi. This is phi. This is phi as well. R squared sine theta, partial theta, sine theta, partial phi, partial theta, plus 1 over r squared, sine theta squared, partial square phi, partial phi squared equals 0. Our purpose is to solve the Poisson's equation. To solve the Poisson's equation, this is not 0. We will introduce the green function. But before that, we should find a complete function set first with orthogonality, with completeness, okay? So how to do that? Let's assume phi of x equals u of r p theta p phi. That's called separation of variable. How do you know? How do you know? Of course, many people try different person try different method, and it works. Personally, using these techniques, we can simplify the calculation a little bit, much more convenient. Therefore, normally we just separate into three parts: R dependent, theta dependent, phi dependence. Keep this in mind. Separation of variable just work for some simple geometry with symmetry. Okay, with symmetry. A simple geometry like infinite space, like a sphere, like a rectangular box, like a cylinder, then we can separate them. It's not for all the case, but it's a very useful case. If we can separate them, we can deal with the problem one by one. We can solve R dependence, theta dependent, and phi dependence one by one. My God. Okay, let's continue. So let's substitute this equation into Laplace equation, and u here, r cancel with this one. So we have p and q. And here we have a sine theta, dp d theta. And because we have another r, remember we have r, we can times r cancel. Okay, so just r squared. And r squared sine theta the same. And this one, we have 1 over r, but once again, so cancel. So what else? We still have two terms. We will divide it by, multiply by r squared sine theta squared because of this one. And UPQ. So by doing so, we can rewrite this equation into this form. Sine squared, because of here, sine squared, 1 over u, pq cancel, r squared, d squared u, dr squared, plus 1 over p sine theta, 1 over uq r squared. So we have extra sine pq sine theta. And here, looks like something wrong. Okay, it's still okay. 1 over q. This part is relatively easy. And we have this part, sine theta. Okay, sine theta. And we have this equation 3.3. In here, we have sine theta here. Sine squared, sine theta squared, sine theta. But if we move sine squared theta to the outside, it will become here. Okay? So u, the same. Theta, q. Looks like we separated them into two parts, part 1 and part 2. Can we further separate them? Yeah. The phi dependence is isolated within these terms. We separate it. So this term must be a constant. Let it be minus m squared. okay, minus m squared. Why we say it's minus? Because it's the angle. Looks like sine and cosine. First derivative, we got cosine. Sine become cosine. Sine become cosine. But second derivative, we will have a minus sine. Okay? So because the phi dependent should be, you change 2 pi, 4 pi, 6 pi, the solution will be the same. Therefore, we know that from our experience, here should be a minus sign. Okay, and we can divide in all terms by sine theta squared. We see that the R dependent is isolated. Inside this one is isolated within these terms. So this term must be a constant. It's an isolated term, R dependent, theta, and move to here. So this term must be a constant. Let it be mu times mu plus 1. Okay? How do you know? I cannot say I just know. From our experience, we solve this equation over and over again in electromagnetism, quantum physics, mathematical physics, over and over again. So it's not surprise to know. It's not a huge surprise to know that. Okay. Let's rewrite equation 3.3 again. This one, let's consider this one first. So it becomes here, the square q d phi. But we remember it's a partial. Oh, because we separated them. So it, from partial derivative becomes total derivative. So the solution for this one is easy. 2 part. Exponential im phi and exponential minus im phi. The equation for p theta, once again, becomes this one divided by this one, right? M squared, p. That's not convenient. Looks complicated. So let's substitute x. Let's let x equals cosine theta. And then the equation takes the form s equals cosine theta. So the cosine theta, maybe I should use x dx equals the cosine theta equals minus sine theta d theta, right? There's a minus sign here. And very ugly. I don't like it, but can we? Okay. Use a pointer. Okay. That's these equations. Then the equation takes the form minus sign here. And remember, this is sine squared. Sine theta d theta becomes minus dx. Minus dx. Okay? Minus cancels. Sine theta becomes 1 minus cosine. Sine theta squared becomes 1 minus cosine theta squared. So becomes these terms. And here we have 1 minus s squared. Okay, this part is the same. P. This equation is called associate Legendre equation. So the solution for this one will be related to the value of mu, and the value of m. So we can write into two parts, p mu m, subscript, superscript. It depends on mu and m. Mu and m, and the variable is cosine theta. Mu and m are to be determined from the boundary conditions. This is the second order differential equation. We should have a two solution. So one is p mu m. The other will be q mu m. Unfortunately, q is in symbol looks like this q, but actually they are completely different. This is the solution for phi dependence. And that's another one. Next page. Okay, so let's rewrite this equation again. And we just solve phi dependent, theta dependent. How about r dependent? R dependent will be relatively easy. The squared u, the r squared here, and r squared mu plus 1u, okay, equals 0. Because we know this one equals here. So the solution for this one will be very easy. R mu plus 1, r minus mu. So take 2 times mu plus 1 mu. Oh, becomes here. Differentiate this one 2 times. Minus mu, minus 1. So they'll multiply, becomes this one. Okay, once again, that's correct. So u over r. Remember, the first term is u over r. So it's r mu, r minus mu minus 1. Okay, so now we can write phi into r mu, r minus mu minus 1, p q exponential im phi exponential minus im phi. The bracket represents a linear combination of the two functions inside. Linear combination of these two functions inside, because the differential equation is linear. The linear combination of any number of solutions is also a solution. This is a linear differential equation. So the linear combination, such as a r mu plus b r minus mu minus 1 times c b mu m c p d q mu m times e exponential im phi plus f exponential minus im phi. And then we will use the boundary condition to determine m, mu. Okay. Next page. But we prefer to solve a simpler equation first. Let's consider the case where m equals 0. Let's as mutual symmetry. As mutual symmetry, Legendre equation and Legendre polynomial. Mathematical property first. m equals 0. So this case will become simpler. This case we can will be much simpler. Okay. So it becomes this one. Second order differential equation. And we will have two solutions, P mu, Q mu. That's the Legendre function of the first kind. That's the Legendre function of the second kind. Here is a pretty good reference. You can check this textbook, table of integrals, series and products, or this one, handbooks of mathematical functions. Okay, we can rewrite the solution. Once again, A and B are coefficients to be determined. And a physical understanding of an equation is unmathematical and imprecise. Here is an example. We don't have to understand, we don't have to solve Q. We just know some properties. One, Q will diverge as X approaches plus and minus 1. X is cosine theta. So when X theta equals 0 and theta equals pi, there will be diverge. So Q mu is not commonly used in physics because of diverge. P mu is finite for X between 1, absolute value of X smaller than 1 and X equals 1. But P mu will diverge. But luckily, unless mu is an integer. So mu is an integer, well, we will have a converge mu close to minus 1. So it's good news. So we don't have to worry too much. Good news. In many physics problems, boundary condition requires mu to be an integer, since the form of Legendre equation is unchanged. If mu changes to minus mu minus 1, then we have these properties. Hence, mu is an integer denoted by L. Okay, so mu is not an arbitrary value, but an integer. Integer. Oh, great. The negative L will become a redundant. So L equals 0, 1, 2, 3. And PL becomes a polynomial. Properties will be shown in the following pages. The range X between 1 and minus 1 considered here is often encountered in physics problems. Mathematically, the range of P mu and Q mu can be extended to the entire complex S plus IY plane. Okay. Here is the behavior, the characteristic of these polynomials. So first is P, PL. We want to confine PL minus 1 to be P mu minus 1 to be finite, to be converged. So L should be integer. 1, 2, 3, 4, 5. Okay? L should be integer. And Q cross 1 and minus 1 will be diverge. It's diverge. It will goes to infinite, goes to infinity, very, very large. So unless we don't have to deal with the problem close to this region, Q are normally skipped. Normally skipped for most of the case. So Legendre polynomials P2 to P5 P0 is a constant, and P1 is from -1 to +1. P2 is something looks like cosine. P3 is something, where is P3? P3 here. Something looks like sine, okay? And P4 looks like P5, once again, up, down, up, and down, up, okay? So Legendre polynomial, in some sense, looks like sine and cosine. Looks like sine and cosine. That's second Legendre functions. Okay. That's why we don't use Q very often, unless the geometry is specially designed and you have to use Q. For most of the case, we don't have to do that. And the set PL is orthogonal. Orthogonal, normal to each other. Okay, that means P, just like this one times this one, and integrate from -1 to 1 will become 0. And this one times this one looks simple because one is even function, the other is odd function, so it's reasonable. But how about P2 times P4? What will happen? Still 0, still 0, because in some region it's positive, but in other region it's negative. So it's still 0. I will show you. And it's orthogonal and complete in index L. Okay, this is very important property of Legendre polynomial. Legendre polynomial tells us PL will become an orthogonal, and there is a complete function set. So any function, any well-behaved function can be expanded as a complete function set. Oh, that makes sense. Our purpose is to show you that. But I don't want to prove this part. You can prove. You have learned this part when you are undergraduate students, or you at electro or at quantum mechanics, because we use this one to solve hydrogen atom, right? It's also complete in index L, okay? And AL is a coefficient to be determined. Then let's come back to another case. N is not equals to 0. So we will deal with complete equation, this equation. This time, M is not 0. This equation is called associated Legendre equation, once again. And X is somewhere between -1 and 1. The solution are UX AP mu M plus BQ mu M. That's called associated Legendre function of the first kind, associated Legendre function of the second kind. Remember, when M equals 0, it's Legendre function of the first kind, Legendre function of the second kind. But M is not 0. We have associate, okay. And A coefficient, B coefficient to be determined. M mu will be determined from the boundary conditions. Okay, let's rewrite the solution again. U A P mu M plus B Q M mu. Once again, luckily, it will diverge when x equals +1 and -1. Hence, it's not commonly used in physics. Once again, we like this conclusion. And P mu m is finite on the interval. Once again, not in the interval. Every point is finite. So we use on the interval. If we just select one or a few points, that's in the interval. Okay. Only when mu is 0 or positive integer. And n ranges from changes from -L to +L. Oh, so mu is integer and 0 or positive integer. And n for each L, if L is 0, m is 0. If L is 1, m will become -1, 0, and 1. If L is 2, m will become -2, -1, 0, 1, 2. So it looks like magnetic quantum number. Looks like principal quantum numbers. And we have another one, angular momentum quantum numbers and spin quantum number. Okay. Under these conditions, we will use this property without proof because electrodynamics, from the viewpoint of electrodynamics, we are user. We will use these properties. Under this condition, we have this one. Okay, so associate Legendre polynomial of the first kind, 0 becomes Legendre polynomial of the first kind. PLM equals -x. Okay. Ooh, so good. PL minus m is -1 m. Oh, factorial. PL, and once again, if m L prime L, that will become delta L prime. Okay, I just show you, this one is simple, and this one is a simple properties. Not very simple, but you can derive these two properties by yourself. Here, you should understand how to use these properties. That's our purpose. Okay, so we can rewrite this one into this form. And these are orthogonal and complete function set. The set PLM is complete in index L. In terms of L, for one index, the sense any function f of x can be expanded as a complete function set. So L runs from m to infinity. M is a fixed integer. I don't expect you to derive this equation by yourself, but keep in mind, PLM is a complete function set. That's it. If you have a chance to deal with PLM, that's good. Just do it. Don't be afraid of dealing with such a complicated polynomial. So we are going to write everything. we write a YLN, theta, and phi. It's a linear combination, it's a product of PLN and exponential IM phi. PLN exponential IM phi. L equals 0 or a positive integer. N minus L to L. So you might learn this one when you learn quantum mechanics. Y00 theta phi 1 over 4 pi square root. Y L equals 1. N equals minus 1, 0, and 1. Okay? Exponential theta, sine theta, exponential I phi, because m equals 1. Cosine theta, sine theta, exponential I phi. So it covers positive n and negative n and positive n. Okay? I should slow down because I provide many information to you. So you should think about this one. However, I will continue and give you more properties without proof. More properties without proof. The property of spherical harmonic, once again, orthogonality relations, -1 to 1, and we can show that the spherical harmonic are orthogonal. That is y L n, L prime m prime complex conjugate, y L n theta phi. Result will be P L L prime, delta L L prime, delta n m prime. Okay, we already have this one, but remember we have this one. We have this one. Only when L and m consider this where m prime m. So only when m and m prime are the same, there will be non-zero. So they are orthogonal. The omega, it means the 0 to 2 pi, the phi, 0 to pi, 0 to 2 pi, 0 here to pi, sine theta, d theta. So the cosine theta from -1 to 1. The phi from 0 to 2 pi. Very close to the end. Yeah, we still have 2 pages to go. Very close to the end. The set YLN theta phi is complete. That is, any arbitrary function g theta phi can be expanded as a complete function set. Oh, g theta phi, arbitrary function of theta and phi, we can expand this one into a complete function set. You just keep this in mind, and you don't have to solve this equation by yourself. We will use this property later on. Just give you a chance to familiar with these properties. That's a complete function set, and m from -L to L, L from 0 to infinity. ALM is the coefficient to be determined. We can multiply both sides by y and m complex conjugate and integrate over theta and phi. And we will do that integrating multiplying, integrating, making use of 3.55, and we obtain this one. The coefficient will be ALM is the omega YLM complex conjugate theta phi. Okay, so we will obtain these coefficients by doing so. Next, we will substitute ALM into this equation. That is, an arbitrary function can be expanded as a complete function set, and coefficient can be determined from here. But remember, we can change here to the omega prime, theta prime, phi prime, theta prime, phi prime, and substitute this one to here. And eventually, you got this one. We got this one. Okay? And obviously, this one, summation here, 0. Integration and consummation are commute. They can change. Okay, YLM here, YLM here, G theta phi here. We change to prime, 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 and prime. Okay, so it's clear. Only when this one equals Dirac delta function. This is connected delta. That means the index, when the index is the same, there will be 1. When the index is different, there will be 0. And this is Dirac delta function. Dirac delta function. This is completeness relations or closure relations. Okay. So completeness or closure relations can be written into this form. And let's relate it to the spatial functions only. Spherical harmonics only. Spatial functions only. And here, just tell you how to, an arbitrary functions can be expanded and in a complete function set. It's just a statement. But here is a completeness or closures relations. Last one, give you more properties. Last properties of YLM, YL minus M, just differ by a minus sign here. A minus sign M, and complex conjugate. YL0, okay? Just like Legendre polynomial. This can be seen from the definition YLM, okay? Minus, plus, minus, minus. Okay. Not very clear, but you can derive this property from here and the relation YL minus M. Today, I give you many informations, maybe too much informations, based on an assumption, based on the assumptions that you learn these properties over and over again. Maybe you are still not familiar with these properties, but you should keep in mind, we solve Laplace equations first and write the Laplace equation in spherical coordinates. And then we use separation of variable to separate R dependent, theta dependent, and phi dependent. And phi dependents are relatively simple. Minus m squared. R dependence also not very difficult. Mu plus 1. Theta dependent, we will derive 2 Legendre equation when m is 0, and associate Legendre equation when m is not equals to 0. is not equal to 0. Okay, and then we can combine theta dependent and phi dependent into a linear combination. That's spherical harmonics. Spherical harmonics. And then I will show you Legendre polynomial are complete function set. Associate Legendre polynomial are complete function set as well. Spherical harmonics are complete function set. And we, as user, we will apply this property to the problems we are going to find. Okay, that's the end of this class. Thank you.